But for people in Brazil, I even myself put E. Yeah, I.
And error correcting codes.
Well, thank you very much to everybody. And first of all, I should thank the organizers for putting together this very nice workshop and for giving me the opportunity to talk. I will be talking about TQFT. So I think in this audience, everybody knows that stands for Topological Quantum Field Theories. Here's the plan of my talk. So first, I will introduce a quantum mechanical model. So it will be 1D TQFT, and I will use categorical definition given by, formulated by Michael Atiyah, so in terms of Atiyah's axioms. But secretly, this one-dimensional TQFT will also be a familiar Chern-Simons theory in 3 dimensions. And well, so the whole story is about applications of these categorical descriptions to quantum mechanics, and to see what you can learn about quantum mechanics, quantum theories in this approach, which uses topology. An example which I chose to talk about today is error correcting codes. And my personal motivation was some results in ADS-CFT correspondence, which talked about holography or ADS-CFT as quantum error correcting codes. So I was trying to understand what they really wanted to say by this, and I decided to use topological theories, Chern-Simons, to discuss a very simple toy model of these error correcting codes. Okay, so this is based on the work with 2 students, Marcos and Luigi, and 2 people from Quantum Information Group, Rafael and Davide. And there is also, if you're interested more details about the method, there is a rather pedestrian review which I put in the archive this year. Okay, so let me start with this definition, categorical definition of a topological quantum mechanical model. So I will start with the Hilbert space, and the Hilbert space will be associated with a set of points. Okay, so set of points represent a Hilbert space. So what are the vectors in this Hilbert space? So the vectors will be all possible ways of connecting these points with one-dimensional objects, so the lines. So these are, first I will think of all possible way of connecting points, and I want to make the story a bit more complicated. So it's not I just only connect the points with lines, but I also want these lines to somehow know about presence of each other, and I can think of this situation as some sort of particles which are evolve in time, and they can interact. This is a one-dimensional system, one-dimensional particles. They can interact, and there are 2 ways they interact, either with some right twists or maybe left twist, and they can also annihilate and disappear. So, okay, so these are, as I said, vectors are all possible connections. And these connections will also know about topological order, also the way the lines cross in a 2-dimensional projection. So how do I define dual space or conjugation and scalar product in this space? So first, to conjugate a vector, I just will mirror reflect it with respect to vertical line. So here the idea is that if you think of the state as evolution of particles, then mirror reflected one will be inverse evolution. And then the scalar product, you just glue the vector and another inverted reflected vector, and this gives you an object which, well, basically when gluing the points disappear, the Hilbert space disappear, so this object is no longer a vector in some space, but it's rather a number. So in general, scalar products will be represented by some knot or link diagram in this case. Okay, so I need to give you some more details about this space. So what is the dimension? So to fix the dimension, so far it's infinite because it's just I want to look at all possible ways the lines can wind in connecting points, but now I will restrict myself to the situation when, well, I will require that this Hilbert space is spanned by all diagrams with no intersection. So I'll call it temporally basis. And why is it temporally basis? Well, here's an example for 4 points. These are only there are only 2 possible ways to connect 4 points without intersections, and then you can think of this as 2 generators of temporally Lieb algebra. I just bend the generators so that there's no begin and end, but they all start from the same line. Yes. So in this particular case, points will be spin 1/2 particles. You can further generalize this, so I will not discuss it today, but these are just spin 1/2 particles. So I said that Hilbert space is represented by points. 4 points in principle is 4 spin 1/2 particles. But the fact that I restrict myself to specific bases here, I'll use only subspace of this 16-dimensional space, only 2-dimensional subspace of this 6-dimensional space. Yeah, I'm not sure I understand correctly the question, but so this is a topological theory, so Hamiltonian is 0, right? So there's no, yeah, so it's there's no evolution. So maybe it will become a little bit clear, but yeah, okay. So I need to explain what I do with all these intersections. So I will use this simplification condition, which says that any diagram with a crossing can be represented by a linear combination of diagrams without crossings with some coefficients. So this is in knot theory, this is called Kane relation, and it appears in this form in works of Louis Kaufman, for example. Obviously the number of points must be even, and if you compute the dimension of the Hilbert space growing the number of points for 2 endpoints, this will be given by Catalan numbers. So this is the naive dimension, so as we will see in a moment that this will give you some upper bound on the dimension, but the actual dimension may be also smaller. So we're coming to the point where we'll really do calculations. So first, the basis which I showed before is not orthogonal, so I need to use Gram-Schmidt procedure to construct orthogonal states. Well, again, you can remember the story of conformal blocks. So this is very similar to conformal blocks, except that the basis which was shown on the previous slide, this basis here, I use 2 conformal blocks in the 2 different channels, in S and T channels. They are not orthogonal in general, so I need to orthogonalize that, and that you can think of these 2 states, this basis 0 and 1. The orthogonal basis now is in terms of normal conformal blocks. Okay, I need to know how to compute overlaps, so that these are overlaps of all basis elements, of these non-orthogonal basis elements, and then, here, so to make this story fun, I will just say that I will use the rules of computing Jones polynomials, because I will always get some knots, and I also want this, I don't want to care about the details of how I draw the diagrams. I only want to care about topology. So Jones polynomials, they're topological invariants, so they will preserve this property. And what are the rules for computing? So any disconnected closed circle, I will just associate a certain number d. So this is number d, appeared also in many talks in this workshop. So this is in fact is something called quantum dimension. So if you close the line, it's like you compute a trace of an identity operator, but it's a quantum dimension, so you compute the quantum trace. And if you have a link, and this link contains a disconnected component, a circle, a trivial circle, you just replace it by a product of this number d and the calculation for the rest of the second component of this link. Okay, so, and then you use also scaling relation shown on the previous slide to reduce any diagram to just collection of disconnected circles and multiply, which are replaced by these d factors. And it's easy to derive this consistency relation that quantum dimension is related to this parameter a of the scaling relation. And here you can also see the Gram matrix, and it's non-trivial. You see that there's certain values of d of quantum dimension when the Gram matrix is degenerate, so it means that the dimension of the span by the basis will be less. So many cases I will assume that this doesn't happen, so we're away from zeros of the Gram matrix. There's a matrix representation that will do the same thing, will calculate the same invariance for you. So here's the this braiding matrix can be realized by this R matrix here. This R matrix will serve as a generator of the braid group, and this U matrix will serve as a generator of a temporal Lieb algebra. And just tensoring these two matrices with identity matrices, you can generate any braid or temporal Lieb algebra. And the relation between the generators of the temporal Lieb algebra and the braid group is here. It is the same scaling relation which appeared before. So the two vertical lines here represent just the identity operator. And in fact, there's a second scaling relation. So you can ask, what if there's the inverse twist, right? So you can just rotate all the diagrams here by 90 degrees, and you'll get the second scaling relation, which expresses the inverse braid generator. Okay, then you can compute all invariants as some sort of matrix element. So you have you can have a braid, or you can have a more general tangle, which is represented by the product of those generator matrices. And then you need to sandwich it between two states. So there are two examples, two states. So I would like to know how to really define these two states in the matrix representation. And the idea is that, okay, this is the temporal Lieb generator, but let's say if I invert this U, then I'll just flip this bra vector and make it a ket vector, right? Then it will be just a tensor product of two vectors. It will be a vector. And in terms of the matrix, it means you can just flatten this metric, and this will give you this tensor product. So I think, yeah, I need to basically compute the square root of the matrix, and I'll find this U will be half of the state here, right? So this U will represent just a cup and not a cap. And there will be some restriction here. So when I conjugate the vector, actually I should do this without complex conjugation. And the reason for that is that the representation is actually pseudo-unitary. The R matrix, the braiding matrix, is not unitary. But this can be cured if I introduce some metric sigma, and I will conjugate the R dagger with these sigmas. That will produce the inverse matrix. So it's a pseudo-unitary representation. And then this is compatible with just transposition of vectors rather than Hermitian conjugation. So here again, when a single vector is just, well, you can, there's certain ambiguity, of course, like choosing signs and phases. Okay, so you can construct any state. First, you can start with a state like this and tensor it with more states like this, and you can generate, well, a typical vector on a Hilbert space with many points, with any even number of points, and then you just apply the generators, the braiding and temporal Lieb generators to produce any other diagram without intersections or with intersections that represent your state. Okay, so that's the general idea. So that's basically everything you need to know about the technique if you want to use this quantum mechanics for your calculation. There's no what? So one interesting observation, which I'm not sure what it really means, is that I can, instead of working with this large representation, so in this representation, the vector on the left, which was one of my basis elements, will be 16-dimensional. But instead of that, I can collapse the matrices, the 4x4 R matrix, to a 2x2 matrix, which will act on conformal block, and this will be a unitary representation. So all the calculations of matrix element of scalar products, in fact, is compatible with two-dimensional unitary representation, but can be realized in a 16-dimensional pseudo-unitary representation. So there is this equivalence between representations. So conformal block basis is somewhat more common in the literature, and this one is unitary, or at least there are unitary representations. Okay, so now I'll pass to the second part, which is really quantum mechanics. And one thing I want to there's one more comment, is the connection with Chern-Simons theory. So since this quantum mechanics gives Jones polynomial, so it's obviously should be the same as SU2 Chern-Simons theory. And this definition, this categorical definition of ATIA, basically is the same thing as just define quantum mechanics in terms of path integral. But mathematicians don't like path integrals, so the whole idea of introduce this definition in terms of categories is to avoid using path integral. So, but this association between, let's say, Hilbert spaces and topological spaces and vectors in these Hilbert spaces with some other topological spaces was based on the idea of the path integral. In particular, if you have if you compute a path integral with a boundary with certain boundary conditions, that will give you a state in the quantum theory, in Chern-Simons theory in particular. So here, how you can identify the states that I showed you before, and the states in Chern-Simons theory. So here, Chern-Simons theory is computed in a three-dimensional space, which is bounded by two spheres, so internal sphere and external sphere. So for me, it's just two boundaries connected by lines. So they can be, lines can connect two boundaries, or they can just go start on one boundary and go back to the same boundary. So these are all different possible states in this Hilbert space, which is associated with a pair of disconnected two spheres. Well, you can of course, compute scalar product by computing the product of path integrals and integrating over the boundary conditions. And this is the association of the parameters. So this is the familiar Q, of Chern-Simons of integrable models. And here's the Chern-Simons level. This is related to this Kaufman variable A through fourth root. Yes. You can try to generalize, but then it's not guaranteed that you will get a nice thing. So you want, I cannot say which, first of all, you need some, you want to preserve topology, so which means that you should be insensitive to certain topological properties, and in terms of knots, there are a set of equivalence relations called Reidemeister moves, right? So you need to say that these two are equivalent, for example, and you want to have a Young-Baxter relation also. And if you do, I think if you modify, I think this is quite a rigid relation. If you try to modify it, even for more general topological theories, Chern-Simons theories, there's no such relation. So it's actually true for SU2 theory. Yes, here's just example. I can put any number of lines. In this case, why I like this example, because Hilbert space associated with 4 points is 2 dimensions, so it's a qubit. So here just have a pair of qubits, and this represents certain entangled state of 2 qubits. I will prefer using qubits because this just gives some familiar intuition, but there's no need to do this, and maybe for some other talk I can talk about my general situation. Okay, now let's talk about quantum entanglement in this description. So I'll just say very basic things. So first, let's consider 2 classes of states. What is important, so here just you have fully connected, well, two boundaries fully connected and 2 boundaries which are disconnected, and of course you want to see this as separable and entangled state. Our more general heuristic picture saying the same thing, so I can have disconnected topology, or I can have a connected topology, and the first case is separable, and the second case is entangled. Well, in Chern-Simons, the story is a bit more complicated because this depends on the dimension which this boundary represents. So if you have here the boundary of S2 with no punctures, it's a 1-dimensional Hilbert space. So this diagram is just equivalent to this diagram. But so you need minimum of 4 Wilson lines connecting the 2 spheres to have an entangled state. And this is, of course, will be maximally entangled state because it's just from any diagrammatic representation, this should represent some kind of identity matrix. Well, so this is a story which I think it's proper calling it categorification. So categorification in my talk will mean that I'll draw diagrams and I'll say, look, this is quantum mechanics. And well, another typical story that emerges in this discussion is relation between space and entanglement. So if you heard that, like ER equals EPR in gravity in the CFT, so this is example of that. So it means that if you have entanglement, you have a space connecting 2 parties. So that's emerging space. Yes. Yeah. So here it's maximally entangled, and this is really minimally entangled, so or not separable, right? Yeah, very good question, and I have an answer on the second slide, on the following slide. Well, so this is a property of states of Chern-Simons theory on a sphere. So you can think of this again in terms of conformal blocks. If you have a sphere with no punctures, then what are the well, Chern-Simons is equivalent to Wess-Zumino-Witten theory. So how many conformal blocks in this theory, in a sphere without punctures? There's only one, this identity block. So it's dimension 1, Hilbert space dimension 1. You can put 2 points. This will be useful in the future. Well, in this case, again, the dimension is 1 because there's only one conformal block, because the representations associated with this 2 punctures should be conjugate. So there's only way of in my language, there's only way of connecting one-way connecting lines. So which means the representations, the charges should be conjugate.
But I guess, I mean, just in terms of the diagram for psi 1, psi 2, why can I not have just the lower half of each of those states?
Okay, yeah, that's an excellent question. So I think you want a diagram like this, right? Yeah, and that's again, that's a property of Chern-Simons theory. That's relation between dimension of the space and number of points is not linear. So that's again will be completely separable state. I'll mention this a bit later as well. This will be so when you have 2 states, or which means that you can, if you insert a completeness relation, you cut the space into 2. Well, then in the middle, what is the Hilbert space in the middle? It's a Hilbert space of a sphere with just 2 points. So it's 1-dimensional. So it's means you can just replace this picture by cutting the lines. Right? That's the property of Chern-Simons theory, and it brings certain complications, which I mention later. Okay, again, so, well, let's do this very trivial classification, answering Javi's question. So this is completely separable. That's completely entangled. And here, well, braiding is a unitary operator. It's a local unitary operation if you with respect to the boundaries. It's a local operation. You apply it on one side, on the other, so it doesn't change the amount of entanglement. So it's again a maximally entangled state. And if you just use the rules that I described earlier, then this is, again, it's just the identity matrix, right? That's one of the Bell states. Okay, here's the non-maximally entangled state. And look, here you have non-local braiding. So to create a braiding like this, you need to exchange lines between left and right. So that's a non-local braiding, non-local operation. Well, you can check that I'm not cheating. So this is a matrix which is not unitary. There's what? I'm not sure what you mean by not invariant. So A needs to be consistent. This is something I didn't mention. A should be a root of unity, so it's a phase. So when you complex conjugate it, A goes to A inverse, and so you can see that this thing represents a non-unitary matrix, and which guarantees that this is not maximal entanglement. And you can study more things. So this is something I will not discuss here. You can, for example, discuss slog classification of bipartite entanglement. So that, in principle, you will apply for any number of punctures. And here you can just reproduce, well, this is some very simple result in terms of maybe quantum information, the bipartite classification. You can also try to multipartite. There things doesn't work that nicely. So certain classes of, let's say, tripartite system of qubits, you don't see the W state because W state turns out to be, so it turns out to be this, simple classification in terms of at the basic level is just too classical to detect a W state. So unfortunately, I will not have time to discuss this here. There's interesting to check what happens with the states in the classical limit. In the classical limit, I would like to claim that, well, the states of Chern-Simons behave something like classical geometries in the ADS-CFT correspondence. And you can derive analog of Ryota-Kayanagi formula. Well, in this level, maybe Ryota-Kayanagi formula will tell you that if you want to calculate how much entanglement between left and right, you need to find a surface which cuts this picture into two by crossing the minimum number of lines. So that will be a minimal surface. Similar story happens in the, you can observe in the tensor network description of ADS-CFT correspondence. And in this classical limit, it's fun to check entropy inequalities like subadditivity. Strong subadditivity is just, it's, I would say, a primary school calculation to derive all these inequalities for this kind of states in for Chern-Simons states in classical limit. Well, okay, so that's a good question. So what happens, as we know, Ryota-Kayanagi formula, sorry. Yeah, the question was, how do I apply, what's the minimal surface that cuts this into two for this state? Because you see there's certain topological defect and it's not clear how to cut it and how many lines you really cut when you cut it. Well, remember that the Ryota-Kayanagi formula works only in the classical limit of ADS-CFT correspondence. And what happens in classical limit with Chern-Simons states, well, the lines do not see each other, they do not interact. So this state, it will be completely equivalent to this state, okay? So in the classical limit, this state, well, you can take A equals 1 limit. So this term will be 0. And this is the classical limit. Yes? Yeah. Well, in principle, yes. Yeah. Yeah, so this is like the interaction and then creation of a pair, annihilation of the pair. The only thing here is that, it is not good to think of this as a time evolution because it's a non-unitary, it represents non-unitary matrix. It's invertible in this case, but it's non-unitary, so it's not a good time evolution. Well, this is even worse. This is even worse because it's a projector, right? So it's non-invertible. No, I mean, why not? I mean, Chern-Simons, it doesn't, I mean, it can give you as a state, this thing exists. So you can think of the state as something, Euclidean preparation. So you have compute Euclidean path integral, and Euclidean path integral, it's fine. You can produce particles. Well, again, that Chern-Simons theory has 0 Hamiltonian, so you will not create anything by evolution. But you can compute this analog of Euclidean path integral, and this Euclidean path integral. I mean, you will not be worried that your evolution is not unitary because it's Euclidean theory. But again, you can compute just path integral of Chern-Simons theory with this insertion of Wilson lines, right? So the only thing to see here is that, well, it's just this diagram represents 2 spheres. You just draw one sphere, and there's another sphere, and your path integral is in the space which fills the space between the 2 spheres. You can insert Wilson line in this upper state. The Wilson lines go like this, okay? And that's just the path integral calculation. Okay, so now I'll just go to applications and quantum teleportations. The first one, just quick reminder what the quantum teleportation is. So we start with Alice, who has a state psi, and she wants to pass the state to Bob. And Bob and Alice, they share two qubits, which are in the maximally entangled Bell state, right? So Alice applies some unitaries first, and then she does measurements, and then she calls Bob and tells the results of the measurement. So if Bob applies certain quantum gates, unitary gates, he converts his qubit into state psi, right? So I suppose this story should be familiar to everybody. Then, yeah, so that's basically the same thing. Now I'll just try to show what this means in the language of these diagrams, right? So as I said in the beginning, Alice has a state, so I do not specify what exactly the diagram, so it's some unknown state. And Alice shares an entangled pair with Bob, so this is a Bell state, right? Now, so if the way to achieve the goal is just basically, let's connect the lines, and then the result will be, so then the Bob will receive the state, right? Well, what does it really mean in quantum mechanics when I connect lines like this? It means I apply a projector on one of the basis states, right? Yeah, so in general, it's not guaranteed that I'll measure. So I need to do, what this says, that I need to do measurement in the basis, in the Bell basis, right? And, but it's not guaranteed that I'll get state called phi plus. I might get a state phi minus or the other psi plus or psi minus. So let's say I measured a different state. So a state which is represented by this braid here. Well, this is not a problem because, well, the result will be this. So this is what Bob will get. But here you have like some unitary operation, and this unitary operation was the same. Basically, you will know it from the measurement. So if you measure this state, you know which unitary operation messed up your state. So you just apply the inverse of this unitary, and you recover the original state. Well, the only problem here is that, well, this state here is not orthogonal. So unfortunately, I cannot complete this story by just drawing you the complete basis of orthogonal state. I'll need to use the Gram-Schmidt procedure, and I'll need to use linear combinations of diagrams, which is not so nice as just diagrams themselves. But in principle, that's the idea. I mean, yeah, again, instead of diagrams, you'll need to use linear combinations of diagrams. Maybe in certain, well, I'm just working for any level of Chern-Simons, any value of k. So maybe for certain choices of k's, at least some of the states like this will be orthogonal, so the situation may be a little bit simpler. Okay, so now this was just a warm-up example. Now I just want to discuss the error-correcting codes and an example which was somehow highlighted in this ADS-CFT correspondence by Almieri, Dong, and Harlow. So they used this quantum information paper by Cleve, Gottsman, and Law to compare quantum error correcting codes with IDS-CFT. So the prime example that they discussed was the state of situation with Q-treats. So let's say we have a state of 3 Q-treats. We'll call it a secret, maybe, or it will be encode some information. So we want to protect this information. We want to pass this information and to split the information between 3 parties, and then be able to the game is, so the information will be split between 3 parties. Every single party will not have any information about the state, but any 2 parties will have full information about the state. And this can be achieved like this. So just take a Q-treat and encode it, map into the state of 3 Q-treats. So this is these basis of 3 Q-treat states, so this is special basis. And then if you, for example, lose one of these Q-treats, which means you only have access to 2 of the 3, then you can always apply a unitary. Let's say the one you don't have access to the 3rd one, apply a unitary on the first 2, so you can find this U quite easily and find that the original state Q-treat can be generated on the first 2 after application of this U. And to achieve this, the state site tilde was selected in a special way, so it has to have certain strong entanglement properties. In particular, well, the 1 Q-treat density matrix should be maximally mixed. And well, this is what I said. So you achieve that no party alone have information. Well, the fact that the matrix is maximally mixed, that means that there's no information contained in the 1 Q-treat density matrix. But any 2 parties, as demonstrated by this application of unitary, can recover completely the information encoded in this state site twiddle. Okay, now in holography, the analog, which was discussed by Almieri, Dong, and Haller, is the following. So, okay, this is the picture of ADS-CFT correspondence, which was also shown in this workshop. So there's a boundary where you have some CFT, and there's a bulk where you have some ADS geometry. And you can think of this actually, now you can imagine an analogy with Chern-Simons. Now in terms of Chern-Simons, I have a sphere, and the sphere may have some degrees of freedom on it. So now my degrees of freedom are these punctures. You can have 4, you can have more. So this is the quantum state in a CFT. Well, in case of Chern-Simons, of course, there's also this correspondence with Wessum and Witten on the boundary. So why do I need the bulk? The bulk can encode for me. It can tell me what the state is. So I can use the bulk to draw a state here. Yeah, well, okay. So I just need the bulk to really say what the state on the boundary is. So that's the analog of ADS-CFT correspondence in terms of Chern-Simons theory. Okay, so in case of error correcting codes, the idea was that, well, this ADS-CFT is a little bit more complicated because you use geometry. So topology is not enough, you use geometry, and geometry is a little bit more complex. So the idea is that degrees of freedom in the bulk, here, for example, I can insert a particle in the center of the ADS space, somehow should be representable on the boundary. And the question is where exactly this information is stored at the boundary. So in fact, the point was that, well, the information is stored non-locally, and it is distributed over the whole boundary in such a way that, well, first of all, if you have here certain subregions, A, B, and C, well, information that B contains is enough to encode everything which is in the causal wedge, or in this case, this is actually entanglement wedge. This is part of the bulk which is limited by the Rieto-Canagio or entanglement surface. So in particular, in this example here you have situation where if you have 3 subregions in the bulk and the particle close to the center, then obviously the information about the particle in the center is not contained in the subregions A, B, and C. But if you take any union, like for example B and C, then the entanglement surface for B and C for the union is this surface. So the particle, the operator O, falls inside the entanglement wedge, and so information about O is encoded on B and C. So this is the analog of this story which I just showed you in the previous slide, that no single party has access to the information, but any pair, any 2 parties have access, complete access to the information in the bulk. Okay, so there's there was a lot of activity related to that. So tensor networks, operator algebra description of bulk reconstruction, and so on. So something I will not discuss here, but I will try to again construct a TQFT version of this story. And so certain case, so first of all, this TQFT description, right? I want to encode a single qubit, but I use 4 spins for that. So it's a redundant description. And so as I said before, if I use 4 spins, the space is 16 dimension, but I only work in the subspace of it. So one thing which I didn't spell out explicitly on the previous slide is that the fact that every subregion which has no information about particle in the center means that the operators, the local operators, they must commute with the operators, with this insertion operator in the center. In a kind of simplified way, you can see it like this. If you just apply a local operation on a qubit, on this topological qubit, if you just use single line, the only thing you can do topologically, you can tie a knot on this line, but this knot actually will commute with everything which is inside. You can just take this knot through this complicated state here, and it will just it will reappear on the other line. So this kind of operation doesn't do anything and cannot recover any information about the state inside. This is a bit trivialized version because in this story any operation like this will be just a phase, so it will not affect the states. But you can generalize it maybe to more complicated cases. Well, a general qubit operation, you need 3 punctures, operation on 3 lines in this diagram. So to construct the analog of this quantum error correcting code, I will use 4 qubits, and the plan is as before. So first you need to I want to use qubits instead of qubits, and I will need 4 qubits. So the first step is to encode this qubit in some non-local way in some highly entangled state, and then you assume that let's assume that some of information is lost, and then you want to recover it on the remaining accessible physical qubits. Okay, so this is my general state which I want to encode, right? So a single qubit I can always write in this non-orthogonal basis, or I can encode it in the computational basis, and this is the relation between coefficients. So maybe for the future it's good to remember that one coefficient is linear in D and the other one is square root of D squared. Okay, so this is the protocol. I have here 4 spheres, so it's a Chern-Simons theory with 4 S2 boundaries, okay? And I want to encode this state in this space. So here is the place where I will encode my state. What does it mean encode? So I kind of take my state and put it in the center, so that the result is this linear combination where I connect lines like this, in the same way as this basis show, and then I just take a linear combinations with coefficients alpha and beta. And now I want to recover, I want to do this trick by losing access to one of these physical qubits on the boundary, and then applying an operation that recovers my information. Well, in some sense, this bulk reconstruction in ADS-CFT correspondence means that I want to be able, by acting on locally, let's say on 1 or 2 or 3 boundaries, to be able to affect, to act on any, to act on this central part and apply any possible unitary in the central part of this chip. Okay, so first the technical step, how do I do encoding? I can start with 5 qubits and then apply the teleportation protocol that I told you before, so that this is my state that I want to encode. Then I do the measurement associated with certain unitary if I choose a proper basis of maximal entangled state. So I might need to remember that there was some unitary generated, which I might need to undo at the end of my exercise. Okay, so let's assume one of the qubits is lost, which means like you physically lost it, or maybe you spilled coffee on your quantum Hall bar, or there's an agent that probably applied some unitary or some operation on one of the qubits, right? Which means that you lose control over like part of your system, and your state is now a mixed state. So the fact that there's some lines that lost somewhere means that your state this is a description of a mixed state. Well, if there were a permutation operator that exchanges points between different spheres, then I can do the following. I can just bring all the available connections and concentrate them on one of the qubits. Here I chose the left one. And let's discard all the rest, which is not entangled with this. And I'll have this diagram. And then I use this property that, if you have only 2 lines connecting my system with the rest, then it means that I can cut, I can basically cut these 2 lines. So 2 lines do not matter. So this is again the same thing, but you can, whenever you can just surround your sphere by another, your system or subsystem by a sphere with which is crossed only by 2 lines, that means that this piece is disconnected. So, which means I would, well, almost solve the problem, because here obviously I will have my encoded state here. The problem, however, that in this case there is no unitary permutation that exchanges points between disconnected spheres. And here is the proof of that. This is the operation that would probably do. This is a natural topological operation that could have done that. But this is not unitary, and here's the proof. So you just multiply it with this Hermitian conjugate. The result of this multiplication is this hole in the middle. So there's a topological defect which does not allow to deform this diagram into a diagram which would represent just an identity operator. And there's probably another way to see the same thing is just to understand that when there's nonlinear relation between number of punctures and the dimension of the space. So when I pass through this section here, which is crossed by 8 lines to 2 spheres with 4 punctures, apparently I'm applying some projection operator. I think there's probably a way to formulate this problem in terms of operator algebra in the language of Marina and Horacio, but I don't know how to do this. So the main obstacle here is that the space is not factorizable. Okay, so first thing I'll try to do, how much time do I have? Do I still have time? I'm almost at the end, but okay, very good. So I can kind of do, I can cheat a little bit. So let's assume that I do a measurement and I measure the upper qubit and lower qubit in this 0 state, right? So this is just this connection of the line, but this gives exactly what I wanted to have. So just here's there's only 2 lines connecting to this remaining part of the system, which I can cut, and the result will be this state, which is the same as the encoded state up to certain unitary. So I can apply this unitary and recover the state. But this is not guaranteed, so this can only happen with certain probability. I think we did the try to well, okay. So far I explained everything just in terms of diagrams, and you can ask, well, and I really did have this question. So, but okay, I mean, can you see this in terms of normal quantum mechanical calculation? Well, okay, yeah, I can indeed write explicitly what this state here is, computing the expansion in the 16-dimensional space. The only relevant part is, well, let's assume that the upper and lower qubit are just here in the middle. This is the left qubit, this is the right one. So I just need these 4 coefficients. They're here. And then I measure the state by projecting on 0, 0, 0 in the middle. And this is the result. So I get a factorized state. So this is, and the first state, if you remember, the first coefficient is linear in D. The other one is square root of D squared. So that's indeed the original state. So that's just, you can use the rules that I explained at the beginning of the talk and see that exactly. So this manipulation with the diagrams does exactly what normal quantum mechanical calculation would do for you. So this is what I understand as categorification. Okay, yeah, so you can compute, actually, I don't know, curiously, if you compute probability to measure this state 0, it's somehow for most of the values of the Chern-Simons level, you get something above 25%, so it's maximum is 9/28. So I don't know what this means. If you measure the states in 0, 1 or 1, 0, then again you get a separable state, which means that, well, the other party doesn't get anything. But if you measure 1, 1, then you're in trouble, then the state is entangled. Okay, so this is an alternative. So now I don't want a probabilistic, I want a really recover information with 100% probability. And so that one way to try doing this is, well, let's just, instead of 4 separate spheres, use 1 single sphere. In this case, the braiding operation will be unitary. But the price to pay that in this case, the space will have huge dimension, and you will only use 16-dimensional space of the space of, well, if you think of spins, then it will be 2 to the 16. It's even more, so it's like 65,000 dimension. And well, from the experimental point of view, this is probably a more natural setup because you can think of quantum Hall and anyons. So what I will do, I'll just braid anyons on a single quantum Hall bar. Well, if I lose access to some of these qubits, some of the anyons in the quantum Hall bar, I can still do some braiding and concentrate all connections in some region on selected set of anyons at the boundary. And this would correspond to some separable states because, well, this is just, this subsystem clearly is separable from the rest. So the state is tensor product. So the only thing I need to understand whether I can extract my original information from this 3 of the 4 lines connected to the center of the chip. And so I know only one answer a positive answer to this question, and here it can be described like this. So if I use this pseudo-unitary representation that I mentioned at the beginning, so this is my state with 4 lines, and I want to really use only 3 lines to recover the information. So this is the structure of the states in this Chern-Simons story. And in particular, if I take this value of A to be 1 of I, so that's this classical limit of Chern-Simons, then the pseudo-unitary representation is also unitary. So then I can just think of really of my qubit, so I can just fractionalize my qubit and now describe it in terms of 4 spins instead of just a single qubit. And then I can find an operation, a unitary, that acts only 3 and that recovers the information about, there is some state encoded here. The question is, can I just distill this state of in just 3 spins of 4? And well, here I do not show explicitly the unitary transformation in this case. it's in our paper, but in this particular case, in the unitary representation, there is one that, which can concentrate this originally encoded state in just a single spin. And okay, this is 100% certain operation. Okay, so that's basically everything that I wanted to talk about, and this is my final messages, right? So what I try to show that you can, well, TQFT states are somewhat useful to describe quantum mechanics in terms of topology, and there is actually some sub-community in quantum information which talk about categorical quantum mechanics and quantum pictorialism. So that's an example of quantum pictorialism where just use pictures to talk about quantum mechanics. But in this case, this is Chern-Simons theory, which from my point of view is more natural than ZX calculus or whatever people use in quantum pictorialism. And well, there's an interesting connection with holography and quantum gravity. So I sometimes try to think of holographic results in holography, well, like Ryota Kanagi, trying to reinterpret this in terms of topological states in this kind of diagrams. There's one practical outcome of this particular study is that I constructed a 4-qubit error correcting code. Thank you.
Thank you, Dmitry, for the nice talk. Questions?
Okay, it's a bit vague and speculative, but maybe let me start by asking, how ergodic is the space? So suppose I pick a particular number of punctures, and I want to think about acting on that Hilbert space by like various braiding operations on maybe on like two of the lines at a time. How much of the Hilbert space do you explore by, I don't know, with some small generating set of those things? You explore the whole thing, is that right?
I think that there are theorems that I mentioned, well, by Friedman and company, Kitaev, that prove that quantum computation, let's say with Chern-Simons, for a certain case, with exceptions of k equals 1, 2, and 4, is universal. So in principle, you can use braiding to explore the. This is how I understand the results.
That's a statement about the action on the logical qubits or on the whole Hilbert space?
The logical qubits.
Okay, I see. So then I guess
it's not certainly not a whole Hilbert space, because topological operations like braiding, they will preserve the this Hilbert, the logical subspace of the full Hilbert space. So you start with 4 spins, but you work only in a 2-dimensional subspace, and braiding will never take you out of this 2-dimensional space.
From the point of view of this qubit realization, it's not
Yeah.
the whole Hilbert space. I see. So then I guess I was wondering, has someone studied a dynamics on the space where you act with random braiding operations? You know, analogous to these random circuits that people study?
Yeah, I think so. I think yes. I cannot give you good references. This is something that I would like to do also. I mean, you can think of this Chern-Simons story as some kind of basis for constructing, well, maybe some spin chain model with real Hamiltonian, because you start with Chern-Simons, which doesn't have any Hamiltonian, 0, but then you can just construct Hamiltonian by just prescribing evolution as certain sequence of application of braiding, right? And it appears in many discussions. I don't know, I had discussions with Madhav Sinha, right, about the way how, well, there's a standard way of generating Hamiltonians from integral models, right? Temporal leap. So here I have temporal leap, I have braid group generators. But you can try to do random. That would be interesting, I think.
So the smallest code is still the Shor 5-qubit code, right? So because this 4-qubit code is probabilistic, right? Or
no, I think here well, I don't know exactly how to let's say what this result that I just showed you, how this corresponds to this statement that the shortest is 5-qubit code, right?
Yeah, the Shor code is supposed to be the smallest quantum error correction code for single qubit error, right?
So what is done here? I let's say I have 4 qubits, and which encode certain qubits.
A
right?
logical qubit, right?
One
There-
logical qubit.
One logical qubit.
So then I assume I lose access to one of the qubits, and then, well, there is certain unit theory that can be applied on 3 remaining ones to recover the original state.
But
So
there is a probabilistic result.
no,
probability-
probabilistic was when I went to the really playing with diagrams. So that was this is my favorite part. So I don't want to write matrices. I
So
want to
it's the
just
smallest is smaller than the Shor code. That's the idea.
So yeah, it would be interesting to understand in which sense, well, it is not. So far it looks yes, but I actually haven't studied the short one. So maybe there is certain condition that is not satisfied, but
Maybe it's a question of which kind of errors you can correct.
Yeah, we're supposed to be
in particular. So,
any error, right? Because he lost a complete.
so some people that saw that, they complain this is not error correction. Well, I think there is some sort of ambiguity in terminology. Error correcting code is not error correction. It's just the way you store the information. And but I think this may be short. I don't know. Maybe this is the why my problem is different from Shor code. Maybe as John said, it's different kind of errors that you can correct. But this is called, I think, erasure correction. So that when you lose one of the qubits, you lose access to one of the qubits, you can restore the information by acting on the remaining part.
More questions? If not, we thank Dmitry again.